In this video, we're going to learn how to solve rational inequalities. We'll first learn how to solve them using a given graph, and then we'll learn how to solve them algebraically. We'll start with the graph problems. So we're going to first solve the inequality x minus 1 over x squared minus 4 is greater than or equal to 0. So this greater than or equal to 0 tells me when is it above the x-axis or equal to 0 on the x-axis. So here I can see that it's above the x-axis from, writing this down, -2 all the way to 1. And I'm going to include 1 since it's equal to 0 there. And then I see it's above the x-axis from 2 onward whenever x is greater than 2. Now I don't include -2 or 2 because those are vertical asymptotes and the function is undefined at those spots. Now, could it be equal to 0 at some other point along this asymptote? The best way to find out is to set your function equal to 0. In this case, x minus 1 over x squared minus 4, and solve that equation, which is multiplying each side by x squared minus 4 leaves me with x minus 1 equals 0, and then x is equal to 0. So the only spot where my function is equal to that horizontal asymptote at y equals 0 is at x equals 1, which I've already included. So my solution is x is any real number such that x is between -2 and 1, or x is greater than 2. If I use interval notation, I would put parentheses -2 comma 1 and then a bracket to include 1 but not -2, and then union parentheses 2 to not include 2 all the way to infinity. And of course you can't include a number that doesn't exist. It's just infinity. So there are two ways to write your solution. Now let's look at the next example. I'm looking for where is x squared minus 4 over x minus 1 squared less than 0. So when it's below the x-axis, but not including 0, that happens between -2 and 1. So -2 is less than x, which is less than 1. And I don't include 1 because that's a vertical asymptote, it's undefined there. And I definitely don't include -2 since it can't equal 0. And then I also notice that it is less than 0 from between 1 and 2. But not including either number because 1 is undefined and 2 is 0. So now if I were to write my answer, I would say that x is any real number such that x is between -2 and 1, or between 1 and 2. Now if I were to write this in interval notation, I want to still exclude that 1 even though it kind of butts up against that same number. So I'll put parentheses -2 comma 1, but don't include 1 or -2, union 1 to 2. This kind of just leaves out that one spot of 1. Now to do this algebraically, you would first have to move everything to one side of the inequality. So I'll subtract 3, and I'll have 4x plus 5 over x plus 2 minus 3 is greater than or equal to 0. And I'm about to do something very similar that I did in the last video, where I'm going to make this my function, and I'm going to find out where this function is equal to 0, and noticing on the graphs where it's also undefined. So to do that, I'm going to set it equal to 0 in a minute, but I actually just want to rewrite this as a proper rational function with just one fraction bar, and not this -3. So I'll actually find a common denominator. That 3 is over and understood 1. So if I multiply the numerator and the denominator by x plus 2, I can get an x plus 2 as a common denominator between both terms. So f of x would equal 4x plus 5 over x plus 2 minus 3x plus 6 over x plus 2. Combining them into one fraction, I can get 4x plus 5 minus 3x and minus 6, because that negative would distribute to both terms, all over x plus 2, so 4x minus 3x is x, and 5 minus 6 is negative 1. So x minus 1 over x plus 2. So when is that greater than or equal to 0? Well, I can make a number line and break it up over all the spots where it's undefined and equal to 0, which would happen to be at negative 2 and 1. 1's where it's 0, negative 2 is where its vertical asymptote is. So I'm going to write these intervals out, negative infinity to negative 2, negative 2 to 1, and 1 to infinity. And I'll pick a number in each of these intervals. So let's say negative 3, 0, and 2. And I'll plug these in to my function, which I'll actually just use its simplified form. So negative 3 minus 1 is negative 4 over negative 3 plus 2, which is negative 1, which gives me a positive 4. Plug in 0, I'll get negative 1/2. And plug it in 2, I'll get 2 minus 1, which is 1 over 2 plus 2, which is 4. So f of 2 is 1/4. So I'll see here it is above the x-axis there, below right here, and above over here. So where is this greater than or equal to 0? Where is this function greater than or equal to 0? Well, at those two outer intervals. So my answer would be x is all numbers such that it is less than negative 2 or it is greater than 1. Now, it could also equal 0. So it's equal to 0 at x equals 1. So I'll include 1, but it's still undefined at x equals negative 2, so I can't include that. The way you can write this in interval notation would be negative infinity to negative 2, but don't include it, union, bracket to include 1 to infinity. Try this as one more example. Let's say we have 6x minus 5 is less than 6 over x. So you'll start by moving everything to one side, giving me 6x minus 5 minus 6 over x is less than 0. So I'm looking for where is this below the x-axis. So I'm looking at f of x is equal to 6x minus 5 over minus 6 over x. And I'll start by finding a common denominator by multiplying these two terms by x over x, giving me 6x squared over x minus 5x over x minus 6 over x. And now that they all have a common denominator by multiplying by x over x, f of x is equal to 6x squared minus 5x minus 6 all over x. And to find out where it's equal to 0 and where it's undefined, I can already tell it's undefined at 0. So I'm going to draw me a number line. I'm going to put 0 on it. And that's where I know it's undefined. But where is it equal to 0? That's where the numerator will equal 0. So I need to factor my numerator. So factoring my numerator, not 6x, it's a quadratic that can factor to two binomials. The in numbers need to multiply to negative 6, and then the outer and the inner need to add to negative 5. So I'm going to use 3x and 2x. And if I do 3x times negative 3, that gives me negative 9, plus 2x times 2, which is 4x, so it would give me negative 9x plus 4x, which is negative 5. So that's how it factors. So I can see it's also 0 at negative 2/3 and at 3/2. That's where it's equal to 0. So my intervals are negative infinity to negative 2/3, negative 2/3 to 0, 0 to 3/2, and 3/2 to infinity. So I can plug in negative 1, negative 1/3, 1, and 2 into my function over here, which is to make sure I don't make any mistakes. I'm going to use a calculator. So 6 times negative 1 minus 5 minus 6 divided by negative 1 gives me negative 5. Then I'll plug in negative 1/3. So 6 times negative 1/3. Move that into the light a little bit more so you can see what I'm typing. Minus 5 minus 6 divided, put that in parentheses, 6 divided by negative 1/3 gives me 11. Then plug in 1, which would be 6 minus 5 minus 6, because that's just 1. So that'll give me f of 1 is negative 5. Then f of 2 would be 12 minus 5, which is 7, minus 6, which is 1. So I can see here that it is below the x-axis, above, then below, and then above to finish. So I'm looking for wherever it's less than 0. So I'm not even looking to see where it's equal to 0, just less. And that happens on this interval. It's below. So negative infinity to negative 2/3. And from 0 to 3/2 is also below. And if you were to write that in set notation, it would be x is all real numbers, such that x is less than, strictly, less than negative 2/3, or between 0 and 3/2. So just to wrap it all up, when you're solving rational inequalities, you're looking for everywhere it's undefined and equal to 0 to kind of make up your intervals to check. And that is how you solve rational inequalities.